In our solar system, Earth shines like a sapphire jewel. We go about our daily lives without knowing that trouble could be coming from deep space. The paths that Earth and most other objects take around the Sun can be predicted. Most of the time, things are quiet and peaceful, but sometimes they get crazy and violent. Earth can be hit by space rocks, zapped by dangerous space weather, jolted and jostled, and threatened by the energy and cosmic forces of other objects. Earth is on a wild ride through space, often in dangerous conditions. When you're moving fast along a predetermined path, you just hope nothing crosses your path, because there's nothing you can do. Rusty Schweickart, a former astronaut, knows how dangerous things in space can be. During the Apollo 9 flight in 1969, he was in charge of the lunar module. He has been issuing warnings about the risks of an asteroid named Apophis that is getting too close to be safe. It grabbed attention because the probability of impact was quite high, significantly higher than any previous impact probabilities. Schweickart recalls a scary real-life example that shows how devastating an asteroid can be, even one smaller than Apophis. On June 30, 1908, at 7 o'clock in the morning, an object about the size of half a football field came hurtling down from space at about 34,000 miles per hour, leaving a fiery trail behind it. Within minutes, the fireball hit Earth's atmosphere and exploded violently over the Tunguska forest in Siberia. The explosion was the largest ever recorded on the planet. It flattened waves of trees and set 8 million of them on fire, covering an area bigger than half of Rhode Island. Since the explosion occurred in a sparsely populated area, no one was directly killed by it. Had the asteroid hit just a few hours later, it wouldn't have struck Siberia, but Europe, and if it had exploded over one of Europe's largest cities, 1 million people would have died. For the last 100 years, the Tunguska explosion has been surrounded by controversy. Many researchers now believe an asteroid was the cause of the explosion, and incredibly, it never even impacted the ground, but exploded 5 miles above Siberia's frozen surface. As it smashed into the lower atmosphere at around 50,000 miles an hour, it was like an egg smashing on concrete. The energy released in the Siberian explosion was equivalent to 15 megatons of TNT, 1,000 times greater than Hiroshima. Over a large city, this would be catastrophic. Scientists call these trespassing objects near-Earth objects. They are comets and asteroids, leftover debris from when the planets formed. The Oort cloud is a part of the Kuiper belt that extends beyond Neptune and is where comets travel. Between Jupiter and Mars, asteroids follow a curved path, though their orbital trips aren't always routine. We don't have to worry too much about asteroids because they orbit in a somewhat orderly belt between Mars and Jupiter. But when one breaks away and all that mass and energy is headed toward Earth, that's when astronomers start to worry. It's not uncommon for cosmic debris to be knocked out of orbit and headed for Earth. Most of it evaporates in our planet's dense atmosphere, but larger objects can break through and crash to the surface. Asteroids are a real and dangerous threat. If you want to look to the cosmos for forces that could end life, just as it has happened before, it will happen again. 65 million years ago, an asteroid the size of a small city plummeted down from the sky. It exploded in the Yucatan Peninsula near the town of Chicxulub in Mexico with a force equivalent to 100 million megatons of TNT. This impact hurled billions of tons of Earth's crust into space, creating a blanket that blocked out sunlight, destroyed the food web, and killed countless species. The cataclysmic impact is thought to have contributed to the extinction of the dinosaurs. We tend to think of asteroids as dangerous, but if it weren't for one, we might not be here today. Our mammal ancestors, once trying to avoid being eaten by Tyrannosaurus rex, were able to evolve after the extinction of dinosaurs. This opened up an ecological niche that allowed mammals to flourish and eventually led to primates and, among them, humans. It's strange to think that the same type of cosmic boulder that allowed humans to thrive could one day wipe us out. In 1998, Congress tasked the National Aeronautics and Space Administration with finding all near-Earth objects at least half a mile across. What they found was unsettling. There are more than 850 near-Earth objects near our vicinity. These asteroids are our nearest and most dangerous space neighbors. Tracking near-Earth objects is a bit like watching storms. Observing them over time gives a better idea of their path, size, and speed. Using telescopic technologies, NASA's SpaceGuard survey has detected over 90% of all dangerous near-Earth objects. These could hit Earth with more power than all the nuclear weapons in the world, potentially triggering mass extinctions. While we wouldn't expect one to hit often, every few 100,000 or million years, if it did, it could wipe out large parts of the population. These rare events can have devastating global effects. If an asteroid hit, it wouldn't only devastate a continent with shock waves but would also throw debris into the air, heating it to 1,000 degrees and causing wildfires across the globe. Even smaller objects could cause disasters. This led Congress to ask the NASA to find all near-Earth objects at least 500 feet in diameter, about the size of the Roman Colosseum. An object that size could wipe out a city or even a small state. Scientists are most concerned about the asteroids they haven't found yet, not the ones they know about. At the moment, there are about 2,000 objects that we can't say for sure won't hit Earth. Fortunately, we now have the technology to prevent near-Earth objects from hitting Earth, giving us the ability to reshape our local solar system for the betterment of life on Earth. The question is, will we end up like the dinosaurs? It's hard to believe Earth has been around for more than 4.5 billion years. Asteroids enter our orbit every year, hitting our planet like a boxer's punches. But one day, Earth could be knocked out. We've learned that near-Earth objects fly by all the time, and we're becoming better at changing our surroundings to protect ourselves. One such rock in space, named Apophis, was discovered in 2004. This pockmarked rock, about 750 feet across, came close to Earth and is scheduled to pass dangerously close again on Friday, April 13, 2029. In 2029, Apophis will get closer to Earth than our communication satellites. If you're in the right place, you'll be able to see it pass by with your own eyes, no binoculars needed. There's a 99% chance Apophis will miss Earth in 2029. However, if it passes at an exact distance of 18,893 miles, it could pass through a gravitational keyhole, a small area in space just half a mile wide. If that happens, Earth's gravity could alter Apophis's path, potentially causing it to hit Earth on April 13, 2036, 7 years later. The gravitational pull of Earth would enlarge Apophis's orbit just enough that it could return and strike Earth. Currently, the chances of this happening are 1 in 45,000. It starts in western Siberia, cuts across and down the Pacific Ocean near California, passes through Central America, and ends in Western Africa. Scientists have developed a scary idea of where Apophis could strike, with a force of more than 1 million megatons of TNT. The asteroid could hit the Pacific Ocean off the coast of California. Such an impact would create a hole in the water 5 miles wide and 9,000 feet deep, causing tsunamis with waves up to 50 feet high to crash into the coast, resulting in unimaginable human loss. A rock 1,000 feet across hitting the ocean is not something we want. Scientists are currently working on ways to prevent such a cosmic disaster. One proposed plan is to blow up the asteroid, but some worry that this could make the problem worse by sending more fragments our way instead of just one. As a result, experts have shifted their focus to altering the asteroid's trajectory. By changing its velocity by just 1/10,000th of a mile per hour, it would miss Earth rather than hitting it. If we detect an asteroid far enough in advance, we can change its path. Although a space probe has already landed on an asteroid, the most challenging idea is launching a manned mission. Once astronauts land on the asteroid, they could attach a radio transponder to track its movements. Now, the United Nations plans to draft a treaty outlining who would be responsible for deflecting killer asteroids. If we continue to neglect this issue, despite knowing that it could happen, that would be a real crime. Any asteroid impact would require an international disaster response. In addition, disaster and emergency management institutions, along with the public, need to be trained to deal with the asteroid threat. It is crucial that everyone understands the level of risk and the potential to eliminate this danger. Furthermore, amateur astronomers can collaborate with scientists to help defend our planet. They can help identify smaller, potentially destructive asteroids hidden in the universe. So, would you like to be an amateur astronomer? Who knows, maybe you could be one of the guardians of our home. On a night in early September 1859, people all over America could see the auroras. They were blood red and so bright that miners in the Rockies thought the sun was rising when they emerged from their tunnels. It was so bright, in fact, that even at midnight, you could read a newspaper. And it didn't just happen in the United States, people around the world saw these auroras. No one knew why it had happened, but earlier that day, an astronomer had noticed something on the sun's surface that he called a white light flare. Back then, the flare and the auroras seemed unrelated, but we now know that the spectacular auroras were caused by that flare, which was a coronal mass ejection. If such a violent event happened again, it could destroy our modern technological world. The sun is the most familiar object in the sky, providing all life on Earth with heat and light. It is so massive that it's hard to imagine, accounting for 99% of the mass in the solar system. This nearly perfect sphere has a diameter of 1.4 million kilometers and has been burning hydrogen and helium for the last 5 billion years. From an astronomical perspective, however, it's nothing special, a G-type main sequence star, also known as a yellow dwarf. But appearances can be deceiving. Solar flares and explosions of plasma particles and radiation travel far into space. We call this phenomenon the solar wind. Solar storms, on the other hand, are more violent eruptions, and the most dangerous type is a coronal mass ejection. A coronal mass ejection has the potential to bring our high-tech society to its knees. Today, we'll learn just how bad a coronal mass ejection could be and what astronomers are doing to monitor the sun in an effort to predict when such an event might occur. Step back in time to 1859, first in Victorian Britain, where it was acceptable for a gentleman to be interested in solar astronomy. One man who took this seriously was Richard Christopher Carrington. Unfortunately, there are no known portraits of him, so we don't know what he looked like. Carrington learned many important things from his observations. He discovered that different latitudes of the sun rotate at slightly different speeds, indicating that the sun is not a solid body but rather a fluid one. He also noticed that sunspots could signal the beginning of a solar storm. On Thursday, September 1st, 1859, the sky was clear in the morning, and Carrington was doing his usual work, observing sunspots. Using his telescope to project the sun's image onto a screen, at 11:18 a.m., he witnessed two brilliant beads of blinding white light appear in what he described as a type of conflagration. Strangely, these bright spots disappeared after 5 minutes with no clear explanation. Carrington had observed a coronal mass ejection, a massive magnetic explosion, a huge cloud of charged particles hurled off the sun's surface. 18 hours later, Earth was hit by an electromagnetic storm, which became known as the Carrington event. At the time, everyone was talking about the beautiful auroras that were visible across the globe. Though some telegraph systems went haywire due to power surges, the event didn't have much impact on everyday life. Remember, this was 20 years before the invention of the light bulb. But today, things would be very different. Coronal mass ejections are common, but they vary in size and direction. The big question is, what are the chances of a Carrington-like event happening today, and how would it affect us? So, what exactly is happening on the surface of the sun when we talk about solar wind and space weather? The sun is composed of magnetic fluid, and as it rotates, it twists and distorts its magnetic field. A twisted magnetic field stores energy, which can lead to eruptions called mass ejections, and these explosions are enormous, sending 1 billion tons of material into space at a speed of 1 million miles per hour. We want to know where these things are going because if they head toward Earth, they could affect the technologies we rely on. For instance, a famous event occurred in Quebec in 1989, where power systems were disrupted for several hours. We've already heard about the Carrington event from the 1800s, but what would happen if such an event occurred today? Our reliance on satellites is extensive now. We use them for global positioning system, communication, weather forecasting, and even financial systems. We also have more extensive power grids and a lot of wireless technology. We don't know exactly how they would react to a massive solar storm. How likely is it that another Carrington event could happen? We know the Sun is still capable of such outbursts. In 2012, there was an event that didn't come toward Earth, but it passed over one of our spacecraft that monitors the solar wind. It pushed all of the spacecraft sensors to their limits, and we now believe it was at least as powerful as the Carrington event, possibly even stronger. It was purely luck that it didn't hit Earth. So, what about predictions? Can we forecast the Sun's behavior a week, a month, or a year in advance? Once a coronal mass ejection is observed, we can start predicting its size, speed, and, most importantly, where it's headed. It all sounds very alarming, and the United Kingdom government is aware of the issue. The National Risk Register lists space weather as a significant threat, comparable to a flu pandemic. Spacecraft engineers are trying to understand the most extreme space conditions so they can design satellites that can withstand such extremes. Both the National Aeronautics and Space Administration and the European Space Agency are preparing to send new satellites into space to study the Sun up close. The United Kingdom's Met Office opened its Space Weather Operations Center in 2014, one of only 3 facilities in the world capable of predicting the Sun's effects on Earth around the clock. For now, there have been very few sunspots, and no significant coronal mass ejections are expected from the side of the Sun facing Earth. Fortunately, this means that for the foreseeable future, our spacecraft, satellites, and power grids are safe. However, in space weather forecasting, the foreseeable future only extends a few days. We still know very little about coronal mass ejections, where they are headed, how big they are, or when they might occur. In the near future, 2 new solar probes will travel closer to the Sun than any spacecraft has ever gone. The National Aeronautics and Space Administration's Parker Solar Probe will approach the Sun's surface, flying through the source of the most energetic solar particles. It will measure the gas and magnetic fields near the Sun to understand why these particles are spreading out into the solar system. Meanwhile, the European Space Agency's Solar Orbiter will investigate how sunspots, flares, and coronal mass ejections on the Sun's surface are related to the solar wind. The success of Solar Orbiter will be crucial for our understanding of the Sun's workings. We believe the Sun's magnetic field is generated similarly to Earth's, but it is much more dynamic and changes constantly. The Sun has an 11-year sunspot cycle during which its magnetic fields shift toward the poles and the polarity flips. The Sun's magnetic field also extends into the solar system, enveloping all the planets. Solar Orbiter will measure these magnetic fields for the first time, giving us the opportunity to observe the fields as they move toward the Sun's poles. To do this, Solar Orbiter will take images of the Sun's atmosphere and measure the number, speed, and temperature of particles moving through the space between the Sun and Earth. However, the magnetometer, which is designed to measure the tiny magnetic fields in space carried by the solar wind, could be one of the most important and sensitive instruments. The Sun is always present in our lives, providing us with light, warmth, and even life itself. For Richard Carrington, who was the first to record a coronal mass ejection, it was simply a strange event. But today, we understand that these occurrences can cause significant damage to the world we live in. With new satellites and more observations, we might be able to learn more about these events and predict when the next coronal mass ejectio will occur. The search for life beyond Earth is still in its early stages, but science has provided an encouraging initial answer. There are plenty of planets in the galaxy, many with similarities to our own. Observations from both the ground and space have confirmed the existence of thousands of planets outside our solar system, and our galaxy likely contains trillions. Yet, so far, we have no evidence of life beyond Earth. Is life in the cosmos easily started and common, or is it incredibly rare? Extraterrestrial life exists. This theory suggests that life exists elsewhere in the universe, possibly even within our own solar system. Microbial life could potentially exist on Mars or the moons of Jupiter and Saturn, for example. More complex life forms, such as intelligent civilizations, could exist on planets orbiting other stars. The Fermi paradox. The Fermi paradox questions why, if intelligent life is common in the universe, we haven't detected any evidence of it. Some theories suggest that intelligent civilizations tend to self-destruct, while others propose that these civilizations are too far away or have no desire to communicate with us. Ancient aliens. This theory proposes that aliens visited Earth in the past and influenced human history and culture. Supporters of this idea point to ancient artwork and texts as evidence of alien visitation. UFO sightings. Unidentified flying objects are often cited as evidence of alien visitation. While many sightings can be explained by natural phenomena or man-made objects, some remain unexplained and could potentially be evidence of extraterrestrial life. Simulation theory. This theory suggests that our entire reality is a computer simulation created by an advanced civilization. Although not directly related to aliens, the theory proposes that the creators of this simulation could be extraterrestrial beings. Let's start by addressing the most basic question: do aliens exist? According to the Drake equation, developed in 1961 by astronomer Frank Drake, the probability of intelligent life existing elsewhere in the universe is high. The equation takes into account factors such as the number of stars in our galaxy, the number of planets that could potentially support life, and the probability of life forming on those planets. Based on these factors, the Drake equation estimates that there could be millions of intelligent civilizations in our galaxy alone. But the question remains, have we ever encountered these civilizations? Many people believe that we have, and there are countless stories of alien sightings, abductions, and encounters. However, there is little concrete evidence to support these claims. Let's now explore some popular theories about what aliens might look like. The traditional image of aliens as small, green, big-eyed beings is a product of popular culture, but it is unlikely that aliens would look anything like this. In fact, it is impossible to predict what aliens might look like because their appearance would depend on the conditions of the planet they evolved on. For instance, if an alien species evolved on a planet with high gravity, they might have shorter, stockier bodies. If they evolved in a harsh, radiation-filled environment, they might have evolved to be more resilient to radiation. It's also possible that some alien species might not even have physical bodies as we know them. They might exist as pure energy or as a hive mind collective. But why would aliens visit Earth? There are a few possible reasons. Some scientists speculate that aliens might be interested in our planet because of its unique location in the universe. Earth is in the Goldilocks zone, where it's not too hot, not too cold, and has the right conditions for life to thrive. Aliens might be interested in studying our planet to learn more about how life can survive in these conditions. Another reason aliens might visit Earth is to make contact with us. If there are millions of intelligent civilizations in the galaxy, it's possible that some are trying to communicate with us. However, if this is the case, they might be communicating in ways we can't even comprehend. Their methods of communication might be vastly different from ours. So, what should we do if we ever encounter aliens? Many scientists believe that any encounter should be approached with caution. We should avoid making sudden movements or aggressive actions, as these might be misinterpreted by the aliens. Instead, we should attempt to communicate peacefully and in a non-threatening manner. If we make contact with aliens, it could have profound implications for our understanding of the universe. It could challenge our beliefs about our place in the cosmos and force us to confront some of the big questions about life, the universe, and everything. Now that we've explored some of the theories and possibilities of alien life, let's consider the idea of the Fermi paradox. This paradox asks the question, if there are so many intelligent civilizations out there, why haven't we seen any evidence of them? Why haven't we detected any signals or observed spacecraft from other worlds? One possibility is that advanced civilizations tend to self-destruct. With technology comes the potential for destruction, whether through environmental damage, war, or some other catastrophe. It's possible that many intelligent civilizations reach a point where they can no longer sustain themselves and ultimately fail. Another possibility is that intelligent civilizations have no desire to make contact with us. Perhaps they simply aren't interested in Earth or in communicating with other species. Or maybe they are too far away to detect our signals, and we are too primitive to detect theirs. Regardless of the reasons, the Fermi paradox remains a mystery and a subject of much speculation. But let's turn our attention to the possibility of life in our own solar system. While we haven't found evidence of intelligent life, there are some promising signs that microbial life might exist on other planets or moons. For example, the NASA Mars rover has detected methane on the planet's surface, which could be a sign of microbial life. Scientists have also found evidence of subsurface oceans on some of Jupiter's and Saturn's moons, which could potentially support life. Now, let's consider the potential implications of discovering intelligent life. If we were to make contact with an alien civilization, it could have profound impacts on our society and our understanding of the universe. For one, it could challenge our existing beliefs and worldviews. We might need to reevaluate our ideas about our place in the cosmos, our religious and philosophical beliefs, and our understanding of the origins of life. It could also raise questions about the ethics of interacting with other intelligent species and the responsibilities that come with such interactions. Another potential impact is on our technology and scientific progress. If we were to encounter a more advanced civilization, we could learn from their technology and knowledge, potentially accelerating our own progress. On the other hand, it could pose a threat if the aliens have hostile intentions towards us. It's difficult to say for certain whether aliens, if they exist, would be dangerous to us. We have no concrete evidence of intelligent extraterrestrial life, and any speculation about their intentions or behaviors is purely hypothetical. Some argue that aliens could be dangerous if they are more technologically advanced and have the ability to conquer or destroy us. Others point out that any civilization advanced enough to travel through space would likely have a more sophisticated understanding of the universe and may be peaceful and cooperative. It's also possible that aliens could be indifferent to us, simply observing us from a distance without any intention of interacting with us. Overall, while it's fun to speculate about the potential dangers of alien life, the truth is that we simply don't know enough to make any definitive conclusions about their intentions or behaviors. The search for extraterrestrial life should be approached with an open mind and a healthy dose of curiosity, rather than fear or paranoia. Regardless of the potential impacts, the search for intelligent life continues. We are constantly developing new technology and refining our techniques to search for signals and evidence of other civilizations. And while the chances of finding intelligent life may be slim, the pursuit of knowledge and discovery is a worthy endeavor in and of itself. That's all for today's topic of aliens. We hope you've enjoyed this discussion and learned something new. If you have any questions or comments, please leave them in the comments section below. Thanks for tuning in, and we'll see you next time. At the beginning, nothing existed. After that, the cosmos began to take shape about 13.7 billion years ago. How this came to be, or if there was ever a time before time, remains a mystery. Yet, physicists have pieced together an approximate timeline of significant events in the cosmos' existence using telescope data and particle physics models. From its beginning to its inevitable demise, we examine key points in the evolution of our universe here. The Big Bang. The Big Bang is a moment in time, not a location in space, from which everything else unfolded. To be more precise, it's the first second of time, the point in history from which all other moments have been measured. Despite its common name, the Big Bang was not an explosion but rather a time when the universe was incredibly hot and dense before space began to expand outward in all directions simultaneously. The Big Bang scenario suggests that the universe started from an infinitesimally small point of infinite density. However, this is merely a convenient way of expressing the fact that we don't know for sure what happened at that time. Our understanding of the universe breaks down at the Big Bang because mathematical infinities don't make sense in physics equations. Cosmic inflation era. Shortly after the Big Bang, the universe rapidly expanded in size in a period known as inflation. During this time, the universe may have expanded exponentially, tearing apart previously connected parts of space. Though mostly theoretical, inflation has gained favor among cosmologists as a possible explanation for the remarkable similarity between distant parts of space. Attempts to detect this rapid expansion through light from the early universe were reported in 2014, but further investigation revealed the culprit to be nothing more than interplanetary dust causing interference. Quark-gluon plasma. The temperature of the early universe ranged between 7 trillion and 10 trillion degrees Fahrenheit just a few milliseconds after the Big Bang. At these extreme temperatures, quarks, elementary particles usually contained within protons and neutrons, were free to move. These quarks combined with gluons, the carriers of the strong nuclear force, in a primordial plasma that filled the universe. Scientists have replicated these conditions using particle accelerators on Earth, though the extreme state only lasted for fractions of a second in both the lab and the early universe. The early epoch. A few thousandths of a second after the Big Bang, the universe continued to expand and cool. During this time, quarks merged to form protons and neutrons. Around 1 second after the Big Bang, the density of the universe decreased enough for neutrinos to travel through space without interacting with other matter. This formed the cosmic neutrino background, which has yet to be directly detected. The first atoms. Protons and neutrons fused together during the universe's first 3 minutes, creating the isotope deuterium, along with helium and trace amounts of lithium. This process ceased as the universe continued to cool. About 380,000 years after the Big Bang, hydrogen and helium atoms captured free electrons to form the first neutral atoms. This event led to the creation of the cosmic microwave background, a remnant of this era first detected in 1965. At this point, photons, no longer colliding with electrons, began to move freely through space. The Dark Ages. Following the formation of the first atoms, the universe entered a period known as the Dark Ages, lasting around 100 million years. During this time, there was no light, as no stars had yet formed. Since astronomers rely heavily on starlight to study the universe, this era remains exceptionally difficult to investigate. The first stars. Roughly 180 million years after the Big Bang, the first stars formed from compressed hydrogen and helium, creating extremely hot cores. These early stars emitted intense photons that ionized the surrounding hydrogen, splitting neutral hydrogen atoms into protons and electrons. This marked the beginning of a period known as cosmic dawn or reionization. Reionization is challenging to study due to subsequent gas and dust masking its signals, but scientists estimate it was completed around 500 million years after the Big Bang. Large-scale structure. Almost a billion years after the Big Bang, supermassive black holes formed at the centers of early galaxies. Intense quasars, visible from 12 billion light-years away, began emitting bright beams of light. Over the next few billion years, the universe evolved further, with gravity pulling denser regions together to form galaxy clusters and filaments of gas and dust, creating a cosmic web. Birth of the solar system. Around 4.5 billion years ago, in one of these galaxies, a yellow star formed from a cloud of gas with rings around it. These rings eventually coalesce to form the 8 planets of our solar system, along with numerous comets, asteroids, dwarf planets, and moons. Earth, the third planet from the Sun, either retained water through this process or received ice and water from comets later on. Earth and humanity. Primitive bacteria appeared on Earth, the third watery world, between 3.8 and 3.5 billion years ago. These organisms evolved into remarkable marine creatures and enormous dinosaurs that fed on plants. Around 200,000 years ago, upright beings emerged, humans, capable of contemplating the vastness of space and learning about the origins of the universe. The end, or not? This isn't necessarily the final chapter. The future of the universe is still a mystery to physicists, depending on our ability to accurately measure the properties of dark energy, the unknown force believed to be accelerating the expansion of the universe. If the universe continues to expand forever, all the stars in all the galaxies will eventually burn out, and even black holes will evaporate into nothing, leaving behind a lifeless cosmos filled with inert energy. Alternatively, there might be a great crunch, where gravity overcomes the expansion driven by dark energy, causing the universe to collapse. Another possibility is the Great Rip, where dark energy accelerates the universe's expansion to the point that it tears itself apart. Galaxies and the universe. We live in a galaxy called the Milky Way, which contains hundreds of billions of stars. How did we get here, and what is the future? These questions relate to galaxies, which are fundamental to understanding the universe. The known universe contains approximately 200 billion galaxies, each unique, immense, and dynamic. Where do galaxies come from? How do they function, and what is their fate? The Milky Way. Our galaxy, the Milky Way, is around 12 billion years old. It's a vast disk with enormous spiral arms and a central nucleus, one of countless galaxies in the universe. Galaxies are massive assemblies of stars, often containing around 100 billion stars each. They are star-forming nurseries, regions where stars are born and die. The stars in a galaxy form in nebulae, clouds of dust and gas. The Milky Way contains billions of stars, many with planets and moons orbiting them. But for a long time, we knew very little about galaxies. The discovery of other galaxies. A century ago, we thought the Milky Way was the only galaxy in the universe. In 1924, astronomer Edwin Hubble changed everything. Using the most advanced telescope of the time, the 100-inch Hooker telescope on Mount Wilson near Los Angeles, Hubble observed faint, hazy patches of light in the night sky. He realized these weren't individual stars but entire star-filled cities, galaxies, far beyond the Milky Way. This was a massive revelation, shifting our understanding from a universe with just one galaxy to one filled with billions. Famous galaxies. For instance, the Whirlpool Galaxy, with over 160 million stars, is known for its enormous spiral arms. The stars of the giant elliptical galaxy M87 shine with a golden hue, indicating it's one of the oldest galaxies in the universe. Then there's the Sombrero Galaxy, with its massive bright core surrounded by a cloud of gas and dust. All galaxies are beautiful, fundamental components of the cosmos, spinning across space like colossal pinwheels. Scale of galaxies. Galaxies are enormous on a cosmic scale. On Earth, we measure distance in miles or kilometers, but in space, astronomers use light years, the distance light can travel in a year. The Milky Way is over 100,000 light-years across, and we are located 25,000 light-years from its center. Despite its vast size, compared to other galaxies, the Milky Way is relatively small. Andromeda, the closest galaxy to us, is about 200,000 light-years wide, making it twice the size of the Milky Way. M87, the largest elliptical galaxy in our cosmic neighborhood, is much larger than Andromeda. But even M87 pales in comparison to IC 1011, the largest galaxy ever discovered, which spans 6 million light-years across, 60 times the size of the Milky Way. The origins of galaxies. Galaxies are not only enormous and ubiquitous, but their origin remains one of the great mysteries in astrophysics. The universe began approximately 13.7 billion years ago with the Big Bang, a moment of intense heat and density. At that time, there were no galaxies. They must have formed from the early universe. Gravity played a crucial role in the formation of stars and galaxies. Around 200 million years after the Big Bang, the first stars emerged, and as their masses clumped together due to gravity, the earliest galaxies formed. Thanks to the Hubble Space Telescope, we can now observe the early universe, when galaxies were just beginning to form. Numerous galaxies are visible through Hubble, but the light we observe from these distant galaxies actually left those objects millions or even billions of years ago. What we see now is the distant past of those galaxies, as it took so long for their light to reach us. The Hubble Deep Field reveals a collection of faint dots, which are very different from the galaxies we see today. These small patches of light are actually millions or billions of stars starting to cluster together. These barely visible blotches represent the oldest galaxies, which began forming about 1 billion years after the Big Bang. However, Hubble's ability to see beyond this point is limited. To explore further back in time, we would need a different type of telescope, one too large to send into space. This telescope could not only identify primordial galaxies but also trace their evolution. By following the development of galaxies and galaxy clusters, scientists can study all the galaxies that have formed since the universe was just a few 100,000 years old. Finally, astronomers can start to answer the question, what did young galaxies look like? Galaxies have evolved from clusters of stars into the complex web of systems we see today, and astronomers are observing this process. As far as we can tell, the largest structures in the universe today began as star clusters, which evolve into galaxies, then galaxy clusters, and eventually into superclusters of galaxies. In the early galaxies, there was a lot of stardust, gas, and irregular structures, but modern galaxies appear organized and orderly. When and how did these chaotic clusters of galaxies transform into neatly structured spirals and pinwheels? The answer lies in gravity. Gravity shapes galaxies, and its effects determine their future. At the center of most galaxies is an immensely strong and destructive gravitational force, and our own Milky Way has one hidden at its core. Over the past 12 billion years, galaxies have taken various forms, from spirals to giant spherical clusters of stars. However, there is still much we don't understand about galaxies. How did galaxies evolve into their current shapes? Were spiral galaxies always spirals? The answer is almost certainly no. Young galaxies are a mixture of stars, gas, and dust, often appearing untidy and chaotic. They begin as chaotic formations, like the Whirlpool galaxy, and over billions of years, develop into more organized structures. The Milky Way wasn't formed from a single galaxy but from a cluster of several. Our Milky Way began as a collection of different formations, objects of various sizes and shapes, that gradually merged to form the galaxy we see today. Gravity is the force that holds these components together. Over time, it slowly draws stars closer, causing them to speed up and flatten into a disk shape. Massive spiral arms collect stardust and gas. This process has occurred countless times throughout the history of the universe. While visually different, these galaxies share one thing in common: they all seem to orbit a central object. For a long time, scientists wondered what could be altering the behavior of galaxies, and they eventually discovered that it was a black hole, and not just any black hole, but a supermassive black hole. The first indication of these supermassive black holes came from detecting extreme amounts of radiation coming from the centers of certain galaxies. These black holes consume their surroundings, much like a giant feast. Gas and stars are the supermassive black holes' meal. Sometimes, these black holes consume so quickly that they shoot energy back out into space as beams of pure energy, called quasars. The presence of a quasar indicates the existence of a supermassive black hole at the galaxy's center. But what about the Milky Way? There is no quasar here. Does that mean there is no supermassive black hole? To find the supermassive black hole at the heart of our Milky Way, scientists study the motion of stars. Just like planets orbit the sun due to gravity, stars also move due to gravitational forces. What we've discovered is a strange and violent environment at the center of our galaxy. Everything is more extreme, and things move very quickly. The stars pass one another at incredible speeds. It's unlike any other place in the universe. Photographs of the stars in orbit revealed a remarkable phenomenon. They must be traveling at speeds of 1 million miles per hour or more. Only a gigantic black hole has the energy to throw large stars around like that. This motion was the conclusive evidence for a supermassive black hole at the center of our galaxy, as it is the black hole's gravity that drives the orbits of these stars. A massive black hole, measuring 15 million miles wide, lies at the heart of the Milky Way galaxy. So, is there any danger to Earth? We are in absolutely no danger of being sucked into our supermassive black hole. It's simply too far away. In fact, the distance between Earth and the supermassive black hole at the center of the Milky Way galaxy is 25,000 light-years, which is many trillions of miles. For the time being, Earth is safe. Although supermassive black holes exert enormous gravitational forces, they are not strong enough to bind galaxies together. In reality, according to the laws of physics, galaxies should be accelerating away from each other. So, what's holding them together? Something even stronger than a massive black hole is at work, something invisible and difficult to detect. It's called dark matter, and it's everywhere. Astronomers have discovered supermassive black holes in the centers of galaxies, which are responsible for the rapid movement of stars in their vicinity. However, these black holes alone are not enough to hold all the stars in a vast galaxy together. So, what is keeping galaxies intact? It remained a mystery until a maverick scientist, Fritz Zwicky, a Swiss astronomer, proposed in the 1930s that something unknown was at play. Zwicky reasoned that galaxies weren't producing enough gravity to stay together, so they should be flying apart. Since their gravity was insufficient, he deduced that there must be something else at work, something never before considered, and he called it dark matter. Fritz Zwicky was decades ahead of his time, which is why he frustrated the astronomical community. But his idea was brilliant, and he was right. It's possible that individual galaxies are also held together by this mysterious substance Zwicky called dark matter. Galaxies rely on dark matter as a sort of protective framework that keeps them from collapsing or drifting apart. Now, scientists have discovered that dark matter does more than just hold galaxies together. It may have also triggered their formation. Scientists believe that after the Big Bang, dark matter began to cluster, and these clumps of dark matter eventually evolved into the nuclei of galaxies. However, the nature of dark matter remains a mystery to physicists. Strange things happen with dark matter, and since we don't know what it is, it's clear that it's not made from the same stuff humans are made of. You can't push against it, you can't feel it, but it's likely everywhere. It's a ghost-like material that can pass right through you as if you didn't exist. Though our understanding of dark matter is limited, it seems to be abundant across the cosmos. In fact, there must be at least 6 times more dark matter than regular matter, the kind humans are made of, in the universe. The way the universe seems to function depends on it. Recently, scientists have indirectly detected dark matter in deep space through a process known as gravitational lensing. Dark matter warps light, and its existence can be tested using gravitational lensing. As a ray of light from a distant galaxy travels toward us, its path bends around a massive concentration of dark matter due to the latter's greater gravitational pull. Some distant galaxies appear stretched and distorted when observed through the Hubble telescope, and this distortion is caused by the presence of dark matter. By carefully examining the forms and degrees of distortion in these galaxies, the importance of dark matter to the cosmos is undeniable now more than ever. It is what makes galaxies form and prevents them from collapsing, even though it's invisible and undetectable. Dark matter rules the cosmos. These galaxies seem to be completely alone. It's true they are trillions of miles apart. But in reality, they exist in groups called clusters, and these clusters of galaxies are linked together into superclusters that contain tens of thousands of galaxies. The Milky Way's place in the cosmos remains a mystery. If you look at the overall image, you'll see that our galaxy is associated with a smaller group of galaxies, consisting of about 30 members in total, and that the Milky Way and Andromeda are the two largest members of this group. Further observation, however, reveals that our galaxy is embedded inside the Virgo supercluster. Researchers are now mapping galaxy clusters and superclusters to better understand the cosmos. Galaxies are immense star empires with shapes ranging from enormous balls to intricate spirals. The problem is that they are always evolving. When we look out into the cosmos, it's easy to assume that our galaxy hasn't changed in eons, but that's not true. The Milky Way is a dynamic galaxy, and over cosmic eons, its basic nature has been changing. Galaxies not only evolve, they also move, and sometimes they run into each other. When they collide, the two galaxies will merge over millions of years. Such collisions happen all the time in the cosmos, and our own Milky Way is no exception. We are on a collision course with the Andromeda Galaxy, and that's terrible news for the Milky Way. At a speed of about 250,000 miles per hour, our Milky Way galaxy will collide with Andromeda in about 5 to 6 billion years. It will be the end for the Milky Way. If you could look out into space, you would see the whole Andromeda galaxy hurtling toward us at a tremendous speed. As the two galaxies interact, both will become more and more disturbed and get closer and closer. There will be a dance of death between them. Whenever galaxies collide, they release clouds of gas and dust in all directions. Their combined gravity tears stars from their orbits and flings them into the void. As doomsday for the Milky Way approaches, the event will be spectacular. The two galaxies will ultimately pass through each other and merge into one. The Milky Way and Andromeda as we know them will cease to exist, and a new galaxy, Milkomeda, will be born, looking like a whole new galaxy. There's no escaping this collision. The question is, what will it mean for planet Earth? We may either be thrown out into outer space when the Milky Way's arms are torn apart, or we could end up inside the heart of this new galaxy. Stars and planets will be flung all over, so this could mark the end of planet Earth. Galaxies across the universe will continue to collide, but this age of galactic cannibalism will eventually end because an even more destructive force exists in the universe, one that nothing can stop. This force will eventually tear the cosmos apart by stretching everything to the point that galaxies are pushed apart from one another. Researchers have identified this new cosmic power. It's called dark energy. Unlike dark matter, dark energy has the opposite effect. It pushes galaxies apart instead of pulling them together. Dark energy, discovered only in the last decade, dominates the universe, but it remains significantly more enigmatic. We don't have the slightest idea why it's there or what it's made of. We know it exists, but beyond that, our understanding is limited. Dark energy is truly strange. It causes things to resist each other and push away as though space itself were filled with tiny springs. In the distant future, scientists predict that dark energy will triumph over dark matter, causing galaxies to drift apart. Due to dark energy, galaxies will eventually die off. It will accelerate the expansion of the universe, forcing all galaxies to move farther and farther away from us until they become invisible and move faster than the speed of light. Therefore, everything else in the cosmos will vanish before our very eyes. The remainder of the cosmos won't vanish today or tomorrow, but it might after 1 trillion years. Galaxies will be left alone in the void. However, this will not occur for an extremely long time. The cosmos is thriving right now, and galaxies are creating favorable conditions for life to exist. Without galaxies, I wouldn't be here, you wouldn't be here, and maybe life itself wouldn't exist. This is fortunate for us, because the only reason life has evolved on Earth is that our tiny solar system was formed in the right region of the galaxy. If we were any closer to the center, we wouldn't be here. Life in the center of a galaxy can be extremely hazardous. In fact, if our solar system were closer to the galaxy's core, it would be so radioactive that it would be impossible for life to continue in any form. Too far from the center would be just as bad. Out there aren't as many stars, and we might not exist at all. We are, in a sense, in the Goldilocks zone of the galaxy, neither too close nor too far away, but just right. There may be millions of stars in this cosmic Goldilocks zone where conditions are just right for life. Furthermore, if our galaxy can support life, then other galaxies might be able to as well. The cosmos is vast, and the most incredible part is that we keep learning new things about it. Every time we think we've figured out the solution to a problem, we discover that it's really part of an even bigger mystery. That's amazing. Our Milky Way galaxy and the galaxies beyond it are full of mysteries and unanswered questions. Who would have guessed 20 years ago that we would be able to identify the black hole at the center of our galaxy? Who would have predicted 20 years ago that the astronomical community would accept the existence of dark matter and dark energy? We should feel amazed to be alive at this particular moment in cosmic history, on this particular planet, on the edge of this particular galaxy, with the ability to ponder questions and seek answers across the whole cosmos. Galaxies are born, they evolve, they collide, and they die. The Milky Way is a fortunate home for intelligent life, and our fate is intertwined with that of every galaxy. Ultimately, our fate is in their hands, as they are the ones who created us and continue to shape our identities. Space has always captured humanity's imagination. Among the celestial bodies that have fascinated us, Jupiter stands out as the largest planet in our solar system. Its vibrant stripes and prominent great red spot make it easily recognizable, but there's more to Jupiter than its size and famous storm. Our understanding of Jupiter has grown exponentially thanks to advancements in space technology and exploration. Jupiter is a gas giant composed mostly of hydrogen and helium, with a diameter approximately 11 times that of Earth. It is so large that over 13 Earths could fit inside it. Despite its size, Jupiter has the shortest day of any planet, rotating on its axis every 9.9 hours. Jupiter's magnetic field is the strongest of any planet in the solar system, generated by electrical currents driven by its rapid rotation and the movement of metallic hydrogen within its outer core. Jupiter's famous bands are high-pressure zones characterized by lighter-colored clouds, while its darker regions are low-pressure zones. The colors we see are due to different types of clouds. Ammonia crystals form the white bands, while other chemicals produce the reddish, brownish, and yellowish hues. As for the Great Red Spot, this iconic feature is a persistent high-pressure region in Jupiter's atmosphere, resulting in a storm that's been raging for at least 300 years. The Great Red Spot is one of the most recognizable features of Jupiter, the largest planet in our solar system. At its widest, the storm stretches to 1.3 times the diameter of Earth, although its size has been shrinking in recent decades. The storm has been continuously observed since the late 19th century, but historical records suggest its existence for at least 300 years. The Great Red Spot is located in Jupiter's southern hemisphere, nestled within a westward-moving jet stream called the South Equatorial Belt. The red color of the Great Red Spot is still a subject of research. It's thought that the color may come from complex organic molecules, red phosphorus, or possibly compounds containing sulfur. However, the exact chemical reactions that give the spot its vivid color remain a mystery. The storm rotates counterclockwise with a period of about 6 days. Interestingly, the rotation speed, size, and color of the spot can change, reflecting the storm's complex interactions with its surroundings. The longevity of the Great Red Spot is intriguing. While storms on Earth last for days or weeks at most, the Great Red Spot has persisted for centuries. This longevity is likely due to Jupiter's rapid rotation and lack of a solid surface, which minimizes frictional dissipation of the storm's energy. The Great Red Spot is a window into the atmospheric dynamics of Jupiter, a gas giant with conditions vastly different from our home planet. Understanding this celestial maelstrom not only unravels the secrets of Jupiter but also sheds light on broader principles governing atmospheres, including our own. Jupiter's four largest moons, Io, Europa, Ganymede, and Callisto, are known as the Galilean moons, named after Galileo Galilei, who discovered them in 1610. Each of these moons is a world unto itself. Io is the most volcanically active body in the solar system, its surface covered in sulfur and sulfur dioxide, giving it a colorful, mottled appearance. Europa has a crust of ice, and scientists believe it might harbor a subsurface ocean, making it a potential site for extraterrestrial life. Ganymede, the largest moon in the solar system, is the only moon known to have its own magnetic field. Callisto, characterized by an extremely cratered surface, is believed to have an ocean beneath its surface. As of my knowledge cutoff in September 2021, Jupiter was known to have 79 moons, though additional moons may have been discovered since then. Saturn isn't the only planet with a ring system, although much fainter and smaller. Jupiter also has rings composed mainly of dust particles from impacts on the planet's small innermost moons. These rings were first discovered by NASA's Voyager 1 spacecraft in 1979. The study of Jupiter has come a long way since Galileo's first observations. Multiple missions, such as Pioneer 10 and 11, Voyager 1 and 2, Galileo, Juno, and more, have been sent to Jupiter to study its composition, magnetic field, and moons. Pioneer 10 and 11 were the first spacecraft to make a close approach to Jupiter, providing valuable data about its radiation belts, magnetic field, and some moons. Voyager 1 and 2 made significant discoveries, such as detecting Jupiter's rings and confirming Io's volcanic activity. The Galileo orbiter spent 8 years studying the planet and its moons, and the attached probe made a direct plunge into Jupiter's atmosphere, providing the first direct measurements of its composition. The Juno mission, still ongoing as of 2021, has made significant contributions to our understanding of Jupiter's internal structure, atmosphere, and magnetosphere. Jupiter, the colossal gas giant, remains a focal point of curiosity for astronomers and space enthusiasts alike. Its impressive size, complex atmospheric dynamics, multitude of moons, and faint ring system make it a fascinating object of study. As we continue to explore Jupiter through telescopic observations and space missions, we unravel the secrets it holds, enriching our understanding of the cosmos. For now, we marvel at the celestial symphony Jupiter conducts, its presence a testament to the intricate, diverse, and vast nature of our solar system. Venus is nearly identical to Earth in size, making it one of our most similar neighbors in the solar system. With a mean radius of about 3,760 miles, or 6,052 kilometers, it's approximately 95% the size of Earth. Its mass is about 81.5% that of Earth. This similarity in mass and size means that Venus also has a comparable density to Earth, approximately 5.24 grams per cubic centimeter, implying a similar rock-iron composition. Venus and Earth have a comparable structure, with a central iron core surrounded by a rocky mantle and a thin crust. The core of Venus, while not as well understood as that of Earth, is believed to be partially liquid, similar to Earth's. This iron core is estimated to be about 2,000 miles in diameter. Above the core lies Venus's mantle, composed of silicate rock that extends up to approximately 1,550 miles from the planet's center, overlaid by a thin crust estimated to be 6 to 12 miles thick. The rotation of Venus is a unique characteristic among the planets of our solar system. Unlike most other planets, which spin on their axes in the same direction that they orbit the Sun, Venus rotates in the opposite direction. This phenomenon isn't fully understood by scientists, but some believe it may be due to a massive collision with a celestial body in the past, which altered the planet's rotational dynamics. Venus rotates extremely slowly, with a sidereal day taking 243 Earth days, the slowest rotation of any planet in the solar system. This slow rotation contributes to the planet's lack of a significant magnetic field. Another quirk of Venus's rotation is that a solar day on Venus is shorter than its sidereal day due to its retrograde rotation and orbit around the Sun. The solar day on Venus is about 116.75 Earth days. The planet's year, the time it takes to orbit the Sun, is about 225 Earth days, which is shorter than its sidereal day. This makes Venus one of the few planets where a day is longer than a year. The surface gravity on Venus is about 90% of the surface gravity on Earth. This means that if you were able to stand on Venus, you would feel slightly lighter than on Earth. However, the extreme atmospheric pressure and temperature would make it impossible for humans to survive without protection. Venus's surface appears to be geologically young, with a relatively low number of craters indicating a surface age between 300 million and 600 million years old. Scientists believe that Venus undergoes a cyclical process where heat from the planet's interior causes the surface to be repaved in a global resurfacing event. There is strong evidence of widespread volcanic activity on Venus. Thousands of volcanoes dot its surface, ranging from less than 1 mile in diameter to over 150 miles. The planet has far more volcanoes than any other in our solar system. However, there is currently no definitive evidence that these volcanoes are still active, although recent studies suggest that some may have erupted within the last few million years. Despite the apparent geological activity, Venus doesn't experience significant tectonic activity like Earth. While Venus does have mountain ranges and rift valleys similar to those seen in tectonically active regions on Earth, it lacks the kind of large, distinct tectonic plates seen on our home planet. This might be due to the planet's slow rotation, which limits the Coriolis effect necessary to drive large-scale tectonic activity. Venus's atmosphere is one of its most distinctive and intriguing characteristics. The atmosphere is primarily composed of carbon dioxide, with most of the remainder being nitrogen. However, there are also traces of other gases such as sulfur dioxide, water vapor, carbon monoxide, argon, and helium. This composition is vastly different from Earth's nitrogen-oxygen atmosphere, making Venus's air toxic to humans and most known forms of life. The atmosphere of Venus is arranged in several layers. The troposphere extends from the surface to about 40 miles up, the mesosphere stretches from the top of the troposphere to about 56 miles high, and the thermosphere reaches up to 125 miles above the planet's surface. Above this, there's a transitional region called the exosphere that merges with the void of space. The high concentration of carbon dioxide in Venus's atmosphere creates a strong greenhouse effect, trapping heat and making it the hottest planet in the solar system, even hotter than Mercury, which is closer to the Sun. The greenhouse gases in the atmosphere absorb heat energy radiated from the Sun, preventing it from escaping back into space. This results in surface temperatures averaging around 467 degrees Celsius, which is hot enough to melt lead. There's very little temperature variation between day and night or between the equator and the poles due to the thick atmosphere's efficient heat distribution. This results in a virtually constant, furnace-like temperature all over the planet's surface. The atmospheric pressure on Venus is enormous, approximately 92 times greater than Earth's at sea level. This is equivalent to the pressure experienced 0.62 miles deep in Earth's oceans. A human exposed to such pressure without protection would be crushed. Despite this, high up in Venus's atmosphere, approximately 31 miles above the surface, the pressure and temperature conditions are similar to those on Earth's surface. Venus's atmosphere is perpetually cloaked in thick, opaque clouds that cover the entire planet. These clouds reflect about 75% of the sunlight that reaches Venus back into space, which is why Venus is so bright and easily visible from Earth. The winds in Venus's upper atmosphere are incredibly fast, reaching speeds of up to 450 miles per hour, much faster than the strongest hurricane winds on Earth. These winds move in a phenomenon known as superrotation, where the atmosphere rotates much faster than the planet's surface. Near the surface, however, winds are much slower, typically less than a few miles per hour. Venus boasts the highest mountain in the solar system, Maxwell Montes, rising 20 kilometers above Venus's mean surface level. The planet's surface is also marked by numerous impact craters, extensive lava flows, and unique surface features like coronae, circular structures caused by the upwelling of hot material from the mantle, and arachnoids, circular structures with a complex pattern of fractures. Due to Venus's slow rotation and dense atmosphere, the planet doesn't experience significant seismic activity like Earth. However, recent studies suggest that Venus may still be geologically active. Venus has been a target of interest since the dawn of space exploration. The Soviet Union's Venera and Vega missions, NASA's Pioneer Venus, and the European Space Agency's Venus Express have all contributed significantly to our understanding of the planet. The Venera program achieved many firsts, including the first human-made device to enter the atmosphere of another planet and the first successful landing on another planet. These missions provided valuable data on Venus's atmosphere and surface. More recently, NASA's Magellan orbiter mapped almost the entire surface of Venus using radar to penetrate the thick cloud cover. This mission revealed details about Venus's surface features and geology. Despite the challenges posed by Venus's harsh conditions, scientists remain interested in further exploring the planet. NASA's planned Veritas and Da Vinci Plus missions aim to study Venus's geologic history and atmospheric conditions, providing insights into whether Venus might have once harbored liquid water or even life. Meanwhile, the European Space Agency's Envision mission will focus on understanding why Venus and Earth took such different evolutionary paths. Japan's Akatsuki mission is currently studying Venus's atmosphere and weather patterns. Venus, our neighboring planet, is an intriguing world of extremes. Its harsh environment poses significant challenges to exploration, yet its similarity to Earth in size and composition, along with hints of potential past water and geologic activity, keep our curiosity alive. As we prepare for new missions to Venus, we stand on the brink of major discoveries that could reshape our understanding of the solar system and our place in it. As a reflection on our own planet's potential future, Venus serves as both a warning and an opportunity for scientific discovery. The universe is a vast and mysterious place filled with countless wonders and secrets waiting to be discovered. Among the many mysteries of the cosmos, one of the most fascinating and profound is the age of the universe itself. Scientists have spent decades studying the universe using a variety of tools and techniques to unravel the mysteries of our cosmic past. Through their efforts, they have determined that the universe is estimated to be around 13.8 billion years old. The search for the age of the universe began in the early 20th century when astronomers first realized that our universe was expanding. The concept of an expanding universe was first proposed by Belgian astronomer Georges Lemaitre in 1927, but it wasn't until the work of American astronomer Edwin Hubble in the 1920s and 30s that the idea was widely accepted. Hubble's groundbreaking observations of distant galaxies revealed that they were moving away from us at great speeds, and that the farther away a galaxy was, the faster it was moving. This relationship, known as Hubble's law, suggested that the universe was not static but was instead expanding. If the universe was expanding, then it must have been smaller in the past, and this realization led scientists to wonder just how old the universe was. The first attempts to estimate the age of the universe were based on models of stellar evolution. Scientists knew that stars undergo a predictable sequence of changes as they age, and they thought that by studying the properties of stars in our own galaxy, they could determine the age of the universe. However, these early estimates were plagued by uncertainties in our understanding of stellar evolution, and they varied widely from a few million years to several billion years. It wasn't until the 1960s that a more accurate method for determining the age of the universe was discovered. In 1964, two astronomers named Arno Penzias and Robert Wilson discovered a faint background radiation that was present in all directions of the sky. This radiation, known as the cosmic microwave background, is thought to be the leftover radiation from the Big Bang, the event that marked the birth of the universe. The discovery of the cosmic microwave background was a major breakthrough in our understanding of the universe, and it provided scientists with a powerful tool for estimating the age of the universe. By studying the properties of the cosmic microwave background, scientists could infer important details about the early universe, such as its temperature and composition. This information, in turn, could be used to estimate the age of the universe. Over the next few decades, scientists refined their measurements of the cosmic microwave background and improved their understanding of the early universe. They also developed more sophisticated models of cosmic evolution, which took into account the effects of dark matter and dark energy, two mysterious substances that make up the majority of the universe. By combining these observations and models, scientists arrived at an estimate for the age of the universe, 13.8 billion years. This estimate has been confirmed by a variety of independent measurements, including observations of distant supernovae and the large-scale structure of the universe. The age of the universe is one of the most well-established facts in cosmology, and it has profound implications for our understanding of the cosmos. The age of the universe tells us that our universe has a long and fascinating history, stretching back billions of years to a time when the universe was just a tiny, hot, and dense singularity. It tells us that the stars and galaxies we see today are the result of billions of years of cosmic evolution, driven by the forces of gravity and the interplay between matter and energy. The universe is estimated to be 13.8 billion years old. Why is the universe still expanding at an accelerating rate? What is the nature of dark matter and dark energy, and how do they shape the evolution of the universe? How did the first stars and galaxies form, and what was the nature of the universe in its earliest moments? These are just a few of the many questions that cosmologists are working to answer. The age of the universe provides a crucial piece of information in the quest to understand the cosmos, but it is just one part of a much larger puzzle. One of the most fascinating aspects of the age of the universe is how it connects to the fundamental nature of space and time. According to Einstein's theory of general relativity, space and time are intertwined, forming a four-dimensional fabric known as spacetime. This fabric can be warped and distorted by the presence of matter and energy, leading to phenomena like gravitational waves and black holes. While the universe is expanding at an accelerating rate today, it is still unclear what the ultimate fate of the universe will be. Some theories suggest that the universe will continue to expand forever, eventually becoming a cold and dark place devoid of stars and galaxies. Other theories suggest that the universe will eventually collapse in on itself, leading to another Big Bang and the birth of a new universe. Whatever the ultimate fate of the universe may be, the age of the universe tells us that we are living in a remarkable moment in cosmic history. We have the opportunity to study the universe at a time when it is still evolving and changing, when stars are still being born and galaxies are still colliding and merging. By studying the universe and its evolution, we can gain insights into the fundamental nature of the cosmos and our place within it. The age of the universe also provides us with insights into the likelihood of intelligent civilizations existing elsewhere in the cosmos. If life is a relatively common occurrence in the universe, and if the conditions for the development of intelligent life are present on other planets, then there may be many civilizations out there that are much older and more advanced than our own. Moreover, the age of the universe has implications for our search for extraterrestrial life. By studying the conditions that led to the emergence of life on Earth, and by exploring the diversity of life forms on our planet, we can gain insights into the types of environments and conditions that might be conducive to the emergence of life elsewhere in the universe. Some theories suggest that the universe is just one of many in a multiverse, a vast and complex network of parallel universes with their own unique properties and histories. The age of the universe tells us that if a multiverse does exist, then there has been ample time for the emergence of many different universes, each with its own unique history and destiny. Finally, the age of the universe reminds us of the incredible beauty and wonder of the cosmos. From the cosmic microwave background radiation left over from the Big Bang to the intricate dance of stars and galaxies across the night sky, the universe is a rich and complex tapestry of phenomena that is both awe-inspiring and humbling. In conclusion, the age of the universe is a remarkable fact that has profound implications for our understanding of the cosmos and our place within it. It tells us about the origins and evolution of the universe, the potential for extraterrestrial life, the nature of reality itself, and the beauty and wonder of the cosmos. As we continue to explore the mysteries of the universe, the age of the universe will remain a key piece of information guiding us in our quest to understand the cosmos and our place within it. A supernova is the largest eruption ever observed by humans. Each detonation is an incredibly brilliant and powerful outburst of a star. One type of supernova occurs as a dying massive star makes its final effort. This happens when a star with at least 5 times the mass of the Sun explodes in a tremendous explosion. Massive stars burn vast amounts of nuclear fuel in their cores, generating enormous amounts of energy and causing the core to become extremely hot. This heat produces pressure, which prevents the star from collapsing. A star maintains equilibrium between two opposing forces, gravity, which tries to compress the star into the smallest, most compact sphere possible, and the outward pressure generated by the burning of nuclear fuel in the star's core. This outward pressure counters gravity's inward pull. When a massive star runs out of fuel, it cools down, causing a decrease in pressure. Gravity then takes over, and the star collapses abruptly. Imagine something with a mass 1 million times that of Earth collapsing in just 15 seconds. The collapse happens so quickly that it produces immense shock waves, causing the outer layers of the star to explode. What remains is typically a dense core and an expanding cloud of hot gas called a nebula. A supernova from a star more than 10 times the size of our Sun might leave behind a black hole, the densest objects in the universe. Now, imagine you are an astronomer at the beginning of the 17th century, before the invention of the telescope. You rely on your limited vision to explore the universe. Then, one day, you witness an extraordinary sight, a new star shining brighter than Venus for several weeks. Its brightness is so intense that it is visible even during the daytime. Over the following months, its brightness diminishes but remains persistent in the night sky. Sky watchers across Europe, the Middle East, and Asia all see the same thing as the German astronomer Johannes Kepler did in 1604. We now know it was not a new star, but a supernova, a massive explosion that occurs when certain stars reach the end of their life cycles. The most recent supernova observed in the Milky Way occurred in 1604. There may have been more nearby supernovas since then, but they have been obscured by interstellar gas and dust, and thus went unnoticed. The Crab Nebula is the remnant of a supernova that exploded thousands of years ago, with its light reaching Earth around the year 1054. The supernova discovered in the Large Magellanic Cloud in 1987 was the closest thing to Kepler's supernova in recent times. Additionally, several supernovas in other galaxies have been recorded. While they can be seen with the naked eye, they are much easier to observe with telescopes. Sky watchers in Kepler's time would have completely missed these distant events. It has now been 418 years since the last observed star explosion in our galaxy. Are we long overdue for a close, brilliant supernova? Scientists predict that between 1 and 3 stars in our galaxy should explode per century. If the next supernova occurs, modern astronomers will be much better prepared for it than Kepler was, or even scientists from just a few decades ago. Today, astronomers have access to telescopes capable of capturing visible light and other forms of radiation. Used together, these tools will simulate the experience of flying close to a supernova and observing it with our own eyes. Additionally, we have telescopes that are sensitive to infrared light with wavelengths beyond the red end of the visible spectrum. Infrared light, with its longer wavelengths, can penetrate gas and dust more easily than visible light, allowing us to observe objects that might otherwise be hidden from view with conventional telescopes. Examples of instruments that primarily capture infrared light include the James Webb Space Telescope. The electromagnetic spectrum includes both visible and infrared light. However, supernovas also emit neutrinos, which are subatomic particles, and modern detectors can capture them. Additionally, astronomers now have detectors that can record gravitational waves, tiny ripples in the fabric of spacetime believed to be emitted by exploding stars. In the scientific literature, two types of supernovas are recognized. A Type 1 supernova occurs when a white dwarf star pulls material from a companion star until a runaway nuclear reaction occurs, blowing apart the white dwarf and sending debris into space. A Type 2 supernova happens when a massive star runs out of nuclear fuel, collapses under its own gravity, and bounces back, setting off a massive explosion. Both types of supernovas can be brighter than the galaxies in which they reside. Type 2 supernovas are particularly fascinating because they emit a tremendous amount of neutrinos, alongside light. Neutrino emissions can actually begin before the explosion. In 1987, when a supernova exploded, 3 detectors were able to record 24 neutrinos, even though neutrino research was still in its early stages. If a supernova were to occur in our galaxy now, the global network of detectors might record hundreds, if not thousands, of neutrinos. Very intriguing signals could be produced if a collapsing star forms a black hole, preventing the explosion from releasing further stellar debris. In such cases, the neutrino stream would suddenly stop. It would be remarkable to observe the sharp boundary of a black hole forming. By comparing data from astronomical databases, we could identify a lost star, which could indicate the birth of a new black hole. The successful detection of gravitational waves from a galactic explosion would complete this puzzle. Gravitational waves, which Einstein predicted would occur when a massive object accelerates, are distortions in spacetime. These signals were first detected in 2015, caused by the merging of black holes and neutron stars. However, a supernova within our galaxy should also produce gravitational waves. For decades, astronomers have used computer models to simulate supernova explosions, but many aspects remain unknown. Gravitational wave data could provide crucial insights into the process. Could a nearby supernova pose a danger to life on Earth? In theory, yes, but the explosion would need to be quite close. Fortunately, there are no stars in our vicinity that are in danger of exploding. If a supernova occurred nearby, its burst of radiation would be catastrophic, making this great news for us. The explosion would release harmful ultraviolet, X-ray, and gamma radiation over several weeks, potentially damaging Earth's protective ozone layer. Even if this radiation didn't reach the ground, without the ozone layer, the sun's deadly ultraviolet radiation would flood the planet, killing everything from oceanic phytoplankton to humans. Some scientists believe a similar event may have occurred around 360 million years ago, near the end of the Devonian period, causing a mass extinction. Supernovas are not just destructive forces, they can also create new life. Astronomers and physicists point out that the nuclear reactions occurring deep within exploding stars create and disperse heavy elements essential for life, such as those that make up our bodies and our world. This means supernovas play a role in the formation of the universe's matter. Supernova explosions will be the new gold standard for astronomers. Volcanoes, too, are powerful natural phenomena. They shape our planet, create new land, and destroy old terrain. Volcanoes release gases that change the atmosphere we breathe, and deep in the ocean, volcanic heat fuels unusual new forms of life. Volcanic activity helps sustain life on Earth, and now we search for signs of volcanoes on other planets. We know that life requires water and energy, and volcanoes produce vast amounts of energy. If we find volcanoes on other worlds, we may also find life. The search begins with our closest neighboring planet, Venus, which bears a close resemblance to Earth. Venus and Earth are similar in mass, and 3 billion years ago, they were almost alike, with new land, new oceans, and atmospheres that could support life. However, on Venus, something went awry. Something caused the history of Venus to diverge drastically from that of Earth. Venus took a definite turn to the dark side long ago. Venus is hell, our malevolent twin planet. Today, the surface of Venus is like a furnace, reaching 900 degrees Fahrenheit, hot enough to melt some metals. So, you stand no chance. Venus is a greenhouse world, with an atmosphere rich in carbon dioxide. It traps solar heat like a blanket. Actual images of Venus's surface reveal a barren, scorched wasteland. The planet was ravaged by its dense carbon dioxide atmosphere, which was produced by volcanoes. Spacecraft orbiting Venus provided the first clues. Radar pierced through Venus's thick clouds, revealing volcanic formations scattered across the planet. These formations closely resemble shield volcanoes on Earth. Shield volcanoes get their name from their shape, round and flat. They ooze lava, sometimes for thousands of years. When we mapped the entire surface of Venus using cloud-penetrating radar, we began examining its landforms and found many similarities to Earth's. In particular, we saw massive shield volcanoes that resembled those in Hawaii. The radar images of Venus were nearly identical to those of Hawaii's shield volcanoes. In the past, Venus was home to volcanoes. Seeing an image of Venus for the first time was astounding. We discovered a cratered volcanic surface, with at least 1,000 large volcanoes, and possibly tens or hundreds of thousands of smaller ones. Lava plains cover 3/4 of Venus's surface, a sign of an ancient catastrophe. This might have once been a place suitable for life, but it was instead consumed by flames. Venus's volcanoes spewed trillions of tons of carbon dioxide into the atmosphere, causing the temperature to soar. The oceans evaporated. On Earth, carbon dioxide can be absorbed by rocks or the ocean. But on Venus, there is no water, and the temperature is so high that carbon dioxide cannot even bond with minerals. Volcanoes ejected carbon dioxide into Venus's atmosphere long ago, and as time passed, fewer and fewer methods existed to remove it. The volcanoes sterilized the planet. If Venus ever supported life, that chance was lost. Earth is the only known planet with life. But that might change with the gas giant Jupiter and its moons, which were once believed to be frozen and lifeless. Yet, a mystery emerges, a cloud hovering over a cold, lifeless world. Upon closer inspection, Venus's volcanoes transformed a planet similar to Earth into a hyperheated inferno. Volcanoes on a planet like Earth were not a surprise, but discovering volcanoes on the Moon was astonishing. In March 1979, the Voyager 1 spacecraft gave us our first close-up look at Jupiter's tiny moon Io, a world we once believed to be frozen and lifeless. And they saw something. They noticed an arc next to the moon, almost like there was a second moon behind it. We were puzzled, asking what it could be. Everyone knew Io was lifeless, dull, and uninteresting. Then people realized, oh my God, it's a volcanic eruption. We discovered that Io is engulfed in volcanoes. It is geologically very active, with constant volcanic eruptions. These eruptions spew vast amounts of sulfur, which gets extremely hot. Sulfur changes color as its temperature changes. It may be red, orange, yellow, or even black. As a result, images of Io's surface resemble a pizza with various types of cheese and olives, where the small black spots are. Io is not dead, it is alive and evolving, with more than 400 active volcanoes. The largest, Pele, erupts from a gigantic lava lake. It extends approximately 400 kilometers into space. It would be an extraordinary sight if we could stand on the edge of that lava lake and observe the plume shooting off into the void of space. Pele's eruptions are so massive because Io is so small. There's nothing to hold the lava back, as Io has virtually no atmosphere and little gravity. These enormous eruptions make Earth's volcanoes seem like fireworks. How can such a small moon be so volcanic? The answer is Jupiter. Just as the moon raises tides in Earth's oceans, Jupiter raises solid rock tides on Io. Io's orbit around Jupiter is not circular. Sometimes it's closer, sometimes farther away. Jupiter exerts a gravitational force on Io, stretching and squeezing it during its 2-day orbit. The ground rises and falls by nearly 300 feet. This constant flexing generates extreme heat and pressure, causing lava to erupt wherever there are weak spots in the crust. Volcanism on Io is planet-scale, unlike on Earth, where only certain areas are volcanically active. Io is essentially one giant hotspot, the most volcanically active body in the solar system, due to Jupiter's immense gravitational power. Volcanic activity on Io has taught us something new. Internal energy sources can drive volcanism in ways that are very different from Earth. Io is a world of lava, extremely hot and violent, making it hard to imagine anything surviving there. We've discovered strange eruptions on numerous planets and moons, but so far, the only world where volcanoes are linked to life is Earth, or so we thought. This is Europa. It orbits Jupiter at a distance of nearly 500 million miles from the Sun and is a 2,000-mile-wide sphere of ice. From afar, its surface appears polished, but up close, it's a different story. Europa is pummeled by Jupiter's immense gravity, just like its companion Io. The surface rises and bends, forming ridges and deep fissures. When we first obtained close-up images of Europa, they seemed vaguely familiar. They resemble Arctic ice flows, and it turns out they are the same. A global liquid ocean lies beneath Europa's several-mile-thick icy crust. Magnetic measurements indicate that Europa's ocean is an astounding 60 miles deep. The gravitational influence of Jupiter heats the rocky interior, melting the ice above. As the core is stretched by tides and heated, possibly melting, it's not unreasonable to believe there is a boundary between a hot core and a liquid water ocean. On Earth, underwater eruptions are surrounded by life. The same may occur on Europa. Here, the darkness is absolute, the pressure a crushing 2,000 Earth atmospheres, a harsh environment, but perhaps a cradle for life. If there is evidence of life on Earth, why not on Europa? It has an energy source, a universal solvent, and complex hydrocarbon chemistry, all the ingredients necessary for life. Life on Europa would be difficult but not impossible. Life exists on Earth in every extreme, from searing heat to crushing pressure and absolute darkness. Life on Europa may resemble life on Earth in unexpected ways. If life exists beneath Europa's ice, it would likely be aquatic but without eyes, as there is no significant light. Organisms might feed off volcanic energy and could use sonar to navigate their surroundings. Volcanoes on Europa could be the cradle of new life. It's conceivable that Europa represents the norm for planets with life, while Earth is the exception. Europa could serve as a model for the billions of moons in the universe with liquid oceans. All of a sudden, our horizons have expanded billions of times by looking at the moons of Jupiter. Our solar system alone is home to more than 170 moons. Multiply this by the size of the universe, and that's a vast number of potential habitats for life. Only liquid water and a source of energy are required, both of which could potentially be provided by volcanoes, which are widespread. This is Saturn, twice as far from the Sun as Jupiter, yet it also has volcanic moons. Similar to Europa, these moons could support life. Saturn is one of the most unique planets in our solar system, with a 600,000-mile-wide ring system and an astounding 62 moons, one of which holds a secret. Enceladus is one of Saturn's more distant and lesser-known moons, long known to be covered in ice due to its highly reflective surface. However, when the Cassini spacecraft visited Saturn, it made a remarkable discovery, not on the planet itself, but on Enceladus. The Cassini probe revealed a massive plume, backlit by the Sun and erupting into space, providing conclusive evidence of volcanic activity. Cassini's sensors zoomed in on the south pole of Enceladus and captured the enormous craters scarring its surface. At the south pole, there are extraordinarily large fissures that open and close as Enceladus orbits Saturn, influenced by tidal forces. These fissures are immense, extending for hundreds of kilometers. When they begin to open, you would see a large crevasse expanding at approximately 100 miles per hour along its length. It would be a spectacular sight. The immense gravitational forces cause the surface to open and contract with incredible speed, generating the heat necessary to melt the ice and form subsurface oceans. The conditions in the water beneath Enceladus's surface are ideal for life. It is at an optimal temperature, and liquid water would resemble seawater on Earth. The chemistry of the water erupting from these fissures suggests that it contains salt and organic matter. As a result, we have identified a location in the solar system where there is a strong possibility that life could exist right now. In the ice particles, Cassini has detected complex carbon molecules in conjunction with liquid water, hinting that life may exist deep within this mysterious moon. Enceladus may not be the only one. Another of Saturn's moons could also harbor life, Titan. Titan is one of the largest moons in our solar system and the only one with a thick atmosphere. It is a frozen world, where ice is as hard as rock and there are lakes of liquid methane. Yet, we may also find evidence of volcanoes and the tantalizing possibility of extraterrestrial life. Volcanoes are among the most destructive forces in the universe, as seen with Io's raging eruptions and Triton's ice and nitrogen explosions. Even on Titan, destruction may lead to the possibility of life. Titan, with a diameter of 3,000 miles, is larger than Mercury. It has the thickest atmosphere of any moon in the solar system, with weather, including cyclones, winds, rain, and even lakes. However, temperatures are so low that liquid methane replaces water. Titan is rich in essential compounds for life, making it one of the most fascinating locations in the solar system. It is an active world and the only moon with a dense atmosphere, one similar to Earth's due to the presence of nitrogen. In Titan's atmosphere, methane gas reacts with sunlight to produce compounds essential to life. But if sunlight continually converts methane into organic compounds, why doesn't the methane run out? Methane is abundant in Titan's atmosphere, yet sunlight should eliminate it quickly. This means there must be a constant source of methane. Something on Titan emits methane in a continuous stream. Cassini has spotted what appears to be a crater, and infrared cameras have revealed different types of material surrounding it. Scientists believe the green areas may be volcanic plains, possibly formed by lava ejected from Titan's interior. On Titan, the liquid emitted by volcanoes could be ammonia or water. Methane and ethane may also be emitted by Titan's volcanoes, which could explain the planet's dense cloud cover and orange atmosphere. This atmosphere likely originated from the outgassing of Titan's volcanoes. Even on a moon as frozen as Titan, volcanoes require heat, and Titan has two sources of it. Radioactive materials heat the interior, and Saturn's immense gravity affects the moon. Like on Enceladus, these two forces produce enough heat to transform ice into water and liquid methane into gas. Could volcanoes on Titan provide a chance for life to survive? The chemical reactions necessary for life as we know it require an atmosphere, a solid surface, liquid water, and heat. Volcanoes could provide all of these on Titan. If life does exist on Titan, it would be truly alien. It might breathe hydrogen instead of oxygen and swim through methane reservoirs at 300 degrees below zero. There may be oceans of ethane, possibly tidal pools, as well as volcanic and hydrothermal activity. Perhaps volcanic heat could generate enough energy to support life on Titan. This is speculative, but it can't be ruled out. However, we may not need to travel so far to discover signs of life. We might find it on Mars, a volcanism-rich world much closer to home. Volcanoes are widespread throughout the solar system on planets such as Io, Titan, and Triton, intricate, volatile, and violent. Once, we believed Earth was the only planet with both volcanoes and life, But now we find volcanoes everywhere, though alien life has yet to be discovered. Volcanoes embody the ultimate forces of creation and destruction, which go hand in hand. It's literally true that if volcanoes hadn't existed, we wouldn't be here either. Volcanic cauldrons are the birthplace of life. They create new landscapes, seed the atmosphere with complex chemicals, and replace the old with the new. If volcanoes are connected to the processes of life, where is life on other planets? Perhaps the origin of the answer lies in ancient times when the solar system was young, on a planet similar to our own, Mars. 3 billion years ago, volcanoes were active there. The greatest volcano in the solar system still stands. Its cliffs rise more than 6 miles high, dwarfing even Mount Everest. This is the formidable Olympus Mons, which covers an area the size of Arizona. Its crater alone is 53 miles wide. A structure of this magnitude takes millions of years to form, a time span Earth's volcanoes never have, since Earth's crust is constantly in motion. In Earth's depths, a stationary hotspot forces magma to the surface, creating new volcanic islands. As the hotspot remains stationary, the surface moves, causing new islands to form and drift away. Mars, however, is different. Its crust is locked solid, with no tectonic activity. The crust is one solid plate, so when a hotspot exists, it stays in place, building larger and larger volcanoes. That's why Olympus Mons is so enormous. Today, Olympus Mons is an icy remnant of a warmer, distant past, a colossal extinct volcano on a fading planet. Due to Mars's diminished atmosphere, the ancient volcanic terrain could one day support life. Evidence of this is visible on Earth. Volcanoes in Hawaii have created enigmatic tunnels known as lava tubes, formed when rivers of molten rock flow into the ocean. Lava tunnels occur when underground rivers of basaltic lava continue to flow beneath a solidified surface, creating a cave-like structure known as a lava conduit. Recent images suggest that Mars's volcanoes may have created similar lava tubes. Any rocky planet with basaltic volcanism is likely to contain these lava channels. After possibly millions of years of inactivity, these lava tunnels could potentially revive life on the red planet. This life may one day be our own. Radiation will be one of the major challenges humans will face when attempting to live on Mars, particularly during solar storms, when incoming cosmic rays can be lethal. The tunnels and caverns of Mars's extinct volcanoes could one day serve as an ideal home, retaining air and protecting us from harmful radiation. A long-dead volcano could help bring new life to a world. Volcanoes are capable of both destruction and creation. The universe is full of strange and surreal paradoxes that challenge our understanding of the world around us. From the mysteries of quantum mechanics to the mind-bending properties of black holes, the universe presents us with a plethora of phenomena that defy our intuition and challenge our perceptions of reality. This video lets you see some of the many things we do not understand in the universe, and the strange and surreal paradoxes in what we think we understand. Everything we know represents just 5% of the universe. What is the rest? Normal matter, protons, neutrons, and electrons, make up just 5% of the universe. Staggeringly, the other 95% is something which we cannot fathom, see, or understand. We call it dark matter, which makes up 27% of the universe, and dark energy, which makes up 68%. But what are these mysterious components of our universe? Dark matter and dark energy are two mysterious concepts in astrophysics that scientists use to explain some of the strange observations we make about the universe. Dark matter is a type of matter that does not interact with light or any other form of electromagnetic radiation. This means that we cannot directly detect it using telescopes or other instruments that rely on light. However, scientists can infer its existence by observing its gravitational effects on visible matter, such as stars and galaxies. Dark matter is thought to make up about 85% of the total matter in the universe, but we still do not know what it is made of. It does not behave like any of the known particles that make up ordinary matter, such as protons and electrons. Some theories propose that dark matter consists of undiscovered particles that do not interact with light or other forms of radiation, while others suggest that it may be made up of exotic objects such as black holes. Dark energy, on the other hand, is a hypothetical form of energy that is thought to permeate all of space and is responsible for the accelerating expansion of the universe. Unlike dark matter, which has a gravitational effect that slows down the expansion of the universe, dark energy has a repulsive effect that causes the expansion to speed up. The exact nature of dark energy is not well understood, but it is thought to be a property of space itself, rather than a type of matter or energy that we can directly observe. Scientists believe that dark energy makes up about 68% of the total energy in the universe. How many dimensions does the universe have? To the best of our knowledge, the universe as we know it has 3 spatial dimensions, length, width, and height, and 1 dimension of time, making a total of 4 dimensions in spacetime. This is known as 4-dimensional spacetime. However, some theories in physics, such as string theory, propose that there may be more than 4 dimensions, possibly up to 11 dimensions. But these extra dimensions are thought to be curled up or compactified, too small to be observed at our scale. This means that although they may exist, they are not directly observable, and their effects on the 4-dimensional spacetime can only be inferred through their influence on the physical phenomena that we can observe. These additional dimensions would help us unify the mathematical bases of the 4 fundamental forces of nature: the strong nuclear force, the weak nuclear force, the electromagnetic force, and gravity. Do these higher dimensions exist, and if they do, is there a way for us to measure their presence? Or will we forever be trapped in our 4-dimensional world? What if our universe is just one of a multitude out there? The idea that our universe is just one of many universes, known as the multiverse theory, is a popular concept in modern cosmology and physics. According to this theory, there may be many other universes existing alongside our own, each with its own unique properties and laws of physics. If this is the case, it would have profound implications for our understanding of the universe and our place in it. For example, it could help explain why our universe appears to be finely tuned to support life, known as the anthropic principle. If there are countless other universes with different physical laws and properties, it would increase the chances of at least one of them being able to support life. The multiverse theory also raises questions about the nature of reality and how we define what is real. If there are many different universes with different physical laws, are they all equally real, or is our universe the only real one? What is time? Time is one of the most difficult properties of our universe to understand. Researchers say that time is a measurable period, a continuum that lacks spatial dimensions. There seems to be an obvious direction or flow of time, and it seems we cannot travel backward in time. Why is this? Are we trapped in the arrow of time, perpetually moving forward? Is the passing of time intertwined with the way our universe works? According to the theory of the Big Bang, time itself began together with the rest of the universe about 13.8 billion years ago. Does that mean it makes no sense to ask what was there before? Time is a fundamental concept in physics and is often defined as the progression of events from the past through the present and into the future. It is a fundamental dimension in which events occur and is often represented as a continuous line or axis. In the context of physics, time is typically measured in units such as seconds, minutes, hours, and years. It is also an essential component of the space-time continuum, which is the 4-dimensional fabric of the universe consisting of 3 spatial dimensions and 1 temporal dimension. The flow of time is often described as unidirectional, meaning that it moves forward and cannot be reversed. This is known as the arrow of time and is often associated with the second law of thermodynamics, which states that entropy, the measure of disorder or randomness in a closed system, tends to increase over time. The nature of time is still a topic of ongoing research and debate in physics and philosophy. Some theories propose that time is an emergent property that arises from the complex interactions of the universe's fundamental components, while others suggest that time is a fundamental property of the universe, akin to space and matter. Particles violating the laws of nature. In certain situations, two particles can seemingly have an instant connection with each other, even if they are located at opposite ends of the universe. This phenomenon is known as quantum entanglement, where two particles become correlated in such a way that the state of one particle is instantly correlated with the state of the other, regardless of the distance between them. While this may seem like a violation of the laws of nature, it is actually consistent with the principles of quantum mechanics. However, it is important to note that this does not allow for faster-than-light communication or the violation of causality. This is because, while the state of the entangled particles may be instantaneously correlated, there is no way to control or manipulate this correlation to transmit information faster than the speed of light. In fact, there is a fundamental principle in quantum mechanics known as the no-communication theorem, which states that it is impossible to use entanglement to transmit information faster than the speed of light. So, while quantum entanglement may seem like a strange and mysterious phenomenon, it does not allow for the violation of the laws of nature or the principles of causality. Could this feature of quantum mechanics one day allow us to send information instantaneously over large distances? Are we alone in the universe? There are at least 2 trillion galaxies in the observable universe, with more stars and planets in them than all the grains of sand on planet Earth. So where is everyone? Why have we not encountered life from elsewhere? Is life incredibly rare, or does it have a limited lifetime, destroying itself before it has had the chance to seek out other life forms? What does this tell us about the future of humankind? The question of whether or not we are alone in the universe is one of the most intriguing and profound questions we can ask. Given the vast size and age of the universe, it seems unlikely that Earth is the only planet with the conditions necessary for life to emerge. There are likely billions of potentially habitable planets in our galaxy alone. However, the fact that we have not yet encountered any definitive evidence of extraterrestrial life is known as the Fermi paradox. There are many potential explanations for the Fermi paradox, including the possibility that life is indeed rare, that it is difficult for life to evolve beyond a certain point, or that intelligent civilizations have a limited lifespan and self-destruct before they can explore the galaxy. It is also possible that we simply have not looked in the right places yet. Our current methods of searching for extraterrestrial life are still relatively limited, and it is possible that more advanced techniques in the future could uncover evidence of life elsewhere in the universe. Does the self-reference problem distort our perception of the universe? We humans are also part of the universe we inhabit, so when we look out to study the stars and galaxies, are we really neutral observers of the universe? When we explore the universe, we are both observers and the subject of observation. How can we pretend to be neutral when we are deeply embedded in what we explore? Could it be that this self-reference problem affects the way we look at the universe and gives us an overwhelmingly wrong impression? The self-reference problem is indeed a complex issue when it comes to our study and perception of the universe. We are not neutral observers of the universe, but rather embedded within it. This self-reference problem can lead to potential distortions in our perception of the universe, as we may unwittingly project our own preconceptions and assumptions onto our observations. For example, we may tend to focus on phenomena that we find particularly interesting or relevant to our own existence rather than taking a more objective and comprehensive approach. By acknowledging our own biases and limitations, we can work to develop more rigorous and objective methods of observation and analysis. Why is the universe seemingly so perfect for us? The universe seems to be perfectly made for us, but why is this? Why do the fundamental constants of our universe, such as the speed of light, have the values that they do, allowing life to exist? Could it be that there are infinite universes with infinite possibilities, and we merely happen to live in one that is perfect for life? There are a few possible explanations for this apparent fine-tuning of the universe. One possibility is the anthropic principle, which states that the universe is the way it is because it must be compatible with the existence of observers. In other words, the universe appears fine-tuned for us because, if it were not, we would not be here to observe it. This is sometimes referred to as the selection effect. Why is it easier to destroy something than to put it back together? Entropy is the amount of disorder, chaos, or randomness in a system. One can never reduce entropy. Everything in the universe slowly moves toward disorder. It is very easy to smash a window, but impossible to put it back together exactly as it was before. The principle of entropy moves the universe from structure to chaos, from an ordered state to disorder. What does this tell us about the fate of the universe? As the universe continues to expand, it will eventually reach a state of maximum entropy, where all matter is uniformly distributed and there is no energy gradient available to drive further processes. This state is known as the heat death of the universe, where the universe will be cold, dark, and lifeless. The universe is not a closed system, as it receives energy from stars and other sources, but the overall trend is toward increasing disorder and chaos. However, it is important to note that this process will occur over an extremely long timescale, likely trillions of years in the future. Can anything escape a black hole? We have observed the effects of black holes, and we have seen one directly. The gravitational force of these massive objects pulls everything toward them, even light itself. What happens in the mysterious, infinitely dense center of a black hole? Could there exist such things as white holes, the opposites of black holes that spew matter and time into our universe? According to our current understanding of physics, nothing can escape a black hole once it has passed the event horizon, which is the point of no return. The gravitational pull of a black hole is so strong that it warps space and time, and anything that crosses the event horizon is inevitably pulled toward the singularity at the center of the black hole, where the laws of physics as we know them break down. We do not know what happens at the center of a black hole, as our current understanding of physics is unable to describe the conditions there. It is commonly believed that the matter at the singularity is infinitely dense and compressed to a point of zero volume, known as a singularity. As for the possibility of white holes, which are hypothetical objects that are the opposite of black holes, there is currently no direct evidence to suggest that they exist. White holes are believed to exist at the other end of a hypothetical wormhole, which is a tunnel-like connection between 2 points in space and time. However, there is no direct evidence to suggest that wormholes exist either. The universe is full of strange and surreal paradoxes. Our quest for understanding these is only just beginning. As we continue to push the boundaries of our knowledge and explore the furthest reaches of space and time, we can be sure that the universe will continue to surprise and challenge us in new and unexpected ways, spurring us on to new heights of discovery and understanding. We used to only know about the planets that circled around our sun, but now we know that there are rocky worlds and huge gas clouds that circle other stars. They have a great story to tell. The early history of these planets would have been very, very violent. Planets are made the same way everywhere. They come from the dust and other materials that are left over after stars are born. So if they are all made the same way, what makes them so different? As it turns out, the universe is full of galaxies, gas clouds, stars, and planets. There are 8 worlds in our solar system, but now we know that they are just a small part of the huge family of planets in the sky. It is a very important moment in the history of science to be sure that there are other systems of planets out there. In our Milky Way galaxy, which has 200 billion stars, there are probably dozens of planets. NASA sent the Kepler Space Telescope into space in 2009 on a 6-year mission to find new planets that orbit other stars. So far, they have found more than 400. Some are huge spinning balls of gas that are 5 times as big as Jupiter. Others are huge rocky worlds many times larger than Earth. Some follow wild, erratic orbits so close to a star that they are burning up. One thing is certain, no 2 planets are the same, each one is unique. But most of these new worlds are very far away and difficult to study. Most of what we know about how planets work comes from the 8 that circle our Sun. Our own planets come in 2 main types. There are 4 rocky planets in the inner solar system: Mercury, Venus, Earth, and Mars. In the outer solar system, there are 4 giant gas planets: Jupiter, Saturn, Uranus, and Neptune. Each of the 8 worlds is very different from the other 7. When our solar system was born 4.6 billion years ago, the planets began to develop their own unique characteristics. When the Sun ignited, it released a massive cloud of gas and dust into space. All 8 planets, including the metal-rich planets closer to the Sun and the gas planets farther away, came from this cloud of space debris. All of the worlds in our solar system are made of the same materials. They are made from the same cloud of gas and dust, but they formed under very different conditions. Some of them formed close to the Sun, where it was much hotter, and some formed far away, where it was much colder. And since the conditions were so different, the things that came out of them were also different. At the beginning of the solar system, there was a pretty even mix of silicates, water vapor, hydrogen, methane, and other elements. These elements in the dust cloud are like ingredients in a cake. They cook in different ways based on how the ingredients are mixed and how hot the oven is. You would mix the ingredients just like you do when baking a cake, then you would put it in the oven, and it would change. This is basically what happened in the solar system. The planet cooks in a slightly different way depending on how close it is to the Sun. Near the Sun, where it is hot, gases are burned off, and water is boiled away. Only materials that stay solid at high temperatures, like metals and rocks, can survive. This is why only rocky planets form close to the Sun. As a planet moves farther away from the Sun, it cooks in a different way. But what kind of planets form depends on what is in the cloud. Based on the type of cloud a solar system forms in, it might not have any rocky planets if there are not enough materials to make something like Earth. Instead, it might have more gas giants or none at all. If you want planets made of rock, you need a cloud full of metals and rocks. The next step is to turn down the heat. As the cloud cools, some of the things in it with a high boiling point start to condense out as solids, and these very small mineral grains begin to form. These tiny pieces of rock and minerals are the beginnings of a new rocky world. They start to stick together over time. If you had one dust molecule and another dust molecule, they would basically hit each other and merge into a slightly bigger dust molecule. This process keeps going, and the particles continue to grow. This process is called accretion. As these particles get bigger, they turn into rocks. Then, rocks slam into other rocks and form boulders. Boulders smash together to form even bigger boulders. At some point, you will have something big enough that its weight is strong enough to start pulling things towards it. So instead of just colliding with things and getting bigger, the growing planet actively pulls things in with its gravity. At first, there were a lot of young planets in our solar system, maybe 100. Most of them did not survive. If you go to the asteroid belt and look at the asteroid Vesta, you can get a good idea of how big a planet has to be before it can pull itself into a spherical shape. Vesta is only 329 miles across, which is not quite big enough to be a sphere. To become round, a growing planet needs to be 500 miles across. Once it reaches that size, it has enough gravity to crush itself into a sphere. Any smaller, and it stays in an irregular shape. Every time a round, young planet crashes into something, it heats up more and more until it begins to melt. Gravity now starts to separate the heavy materials from the lighter ones. Lighter materials tend to float up and form a crusty layer, while heavier materials, like metals, sink down and form a dense core at the planet's center. Finally, the young planets start to look like proper planets. But now, they must survive a period of violence and destruction, a brutal time that will determine which planets will survive and which will perish. After the Sun was formed, all 8 of our planets emerged from the same cloud of dust and gas, but they turned out to be very different. There was no real plan for how each of the new planets should be made. They followed the rules of physics and chemistry, but most of what happened was just a matter of luck. About 4.5 billion years ago, our Sun was surrounded by about 100 young planets. It turned into a demolition derby, planet collided with planet, and most were wiped out. The early history of these planets would have been very, very violent, with many of these collisions happening in the last stages of each planet's growth. As these collisions occurred, some planetesimals began to grow at the expense of others. These growing bodies eventually became planets, growing larger and larger as they absorbed the smaller planetesimals around them, causing a lot of space debris to hit the surface of the protoplanets. After the chaos, only 4 rocky planets remained. Due to the unique events that happened to each planet in the past, they are all vastly different from each other. Mars is a frozen wasteland, Earth flows with liquid water, Venus is full of volcanoes, and Mercury is small, empty, and very hot. A huge crash, for instance, might have impacted Mercury, leaving it with a thin crust and a dense core, suggesting that it might have been a larger planet in the past until something hit it and stripped away its lighter crust, leaving only the dense center. Earth, too, experienced a significant collision during its development. It was hit by another object, which tore apart part of its mantle and sent pieces into orbit around the Earth. These pieces eventually came together to form the Moon. Mars also appears to have experienced a major impact. Its crust is thinner in the northern hemisphere than in the southern hemisphere. One theory suggests that an impact in the planet's early history blew off much of its northern crust, leaving it to build up again in the south. There were 2 major outcomes from all of these collisions. First, they reduced the number of baby planets that survived. Second, they brought more materials to the planets that did survive. If a planet collided with a metal-rich body, those metals would tend to sink down into the planet's forming core. However, if it collided with something lighter or icy, that material would tend to stay on the surface and become part of the crust. Closer to the Sun, 4 rocky planets were almost finished forming. They had solid cores of hot iron, surrounded by layers of liquid iron, with a shell of molten rock and a crust on top. All of these rocky planets were made from the same basic materials, but each one turned out very different in size and destiny. Space might look empty, but it's not. It's full of particles blown out by the Sun's strong magnetic fields created by the Sun rise up in giant loops above its surface. When these loops hit each other, a storm of very hot, highly charged particles shoots out into space, called the solar wind. Astronauts can even see it when they close their eyes. When you close your eyes, sometimes you see a little flash of light, and that flash is caused by an energetic particle passing through your head and interacting with the fluid in your eye. Astronauts in space can see these flashes every few minutes. The solar wind could kill astronauts if they were exposed to a large amount of it. During the Apollo program, there was an explosion on the Sun between 2 moon missions that would have killed the astronauts had they been in space at the time. Radiation in space is a big concern. However, here on Earth, the solar wind doesn't pose much of a threat, because we are protected by an invisible magnetic field generated from the center of the Earth. Magnetic fields are created by motion, converting motion into magnetic energy. Deep inside the Earth, the hot, liquid metal flows around the solid core, turning this energy into a magnetic field that extends out from the poles. This field deflects the solar wind, preventing it from reaching Earth's atmosphere or the surface. If a planet has a magnetic field, it will push the solar wind away. Earth's magnetic field protects the atmosphere and everything living on the surface. Sometimes, the magnetic field can get disrupted, leading to spectacular light shows called auroras over the poles. Without a magnetic force field, Earth's atmosphere and water would be blown away by the solar wind, leaving a planet that is dead and dry, much like Mars. Mars was formed in a similar way to Earth, but today it's cold, dry, and relatively inactive. So why have the 2 planets changed so much? NASA sent 2 robots, Spirit and Opportunity, to Mars in 2004 to explore its surface. They revealed that Mars is a dry and hazardous desert with only a fraction of Earth's atmosphere. However, they found evidence that water once existed on Mars. Mars wasn't always a barren, dry place. There is strong evidence that water once existed below the surface, occasionally rising to the surface before evaporating. In some areas, we can even see ripple patterns in the sand, which form when water flows over it. This suggests that not only was there water underground, but it also flowed across the surface. If Mars once had water, it likely also had a thick atmosphere. So what happened? We know that Mars once had volcanoes, indicating a hot interior. Because Mars was made of the same materials as Earth, it likely had a hot iron core surrounded by liquid metal, which would have generated a magnetic field. The big question is, where did the magnetic field go? Early in Mars' history, the planet probably had a strong magnetic field, likely created in the same way as Earth's. But Mars is smaller than Earth, so it loses heat more quickly, meaning that its liquid core could have solidified sooner. When the core froze, convection stopped, halting the flow of molten metal and causing the magnetic field to disappear. Without the protective magnetic shield, the solar wind stripped away Mars' atmosphere, and the water evaporated, turning Mars into the cold, desolate planet we see today. The rocky planets, Mars, Earth, Venus, and Mercury, formed within 150 million miles of the Sun. However, 4 times farther out, the Sun heated a very different kind of planet. These massive planets, made mostly of gas, have no solid surfaces at all. So far, astronomers have discovered over 400 planets in distant solar systems, and nearly all of them are enormous gas giants. Our solar system contains 4 of these gas giants, Jupiter, Saturn, Uranus, and Neptune, all of which have thick, dense atmospheres composed of hydrogen, helium, and methane. So why are the outer planets made of gas, while the inner ones are rocky? It's very cold 500 million miles from the Sun. In the early solar system, this region had some dust but was mostly gas and water frozen into ice grains. It was cold enough to make solid ice, where the giant planets began to form. We think that ice snowflakes stuck together to form the cores of the gas giants, which is why they grew so large. There was so much ice and gas that their cores became about 10 times the size of Earth. These massive cores generated a lot of gravity, which pulled in the surrounding gas, creating thick, soupy atmospheres that extended tens of thousands of miles deep. The more gravity the planets had, the bigger they became, pulling in even more dust and debris, which formed their moons. Both Jupiter and Saturn have more than 60 moons each. The gas giants have another feature that sets them apart: rings. Saturn is known for its beautiful rings, but Jupiter, Uranus, and Neptune also have rings, though they are faint and difficult to see. All 4 gas giants have rings, but Saturn's are the most prominent. From afar, Saturn's rings appear as a single flat disk, but in reality, they are made up of thousands of small rings, each only a few miles wide. When the Cassini probe passed by, it discovered that billions of pieces of ice and space debris were moving within the rings at speeds up to 50,000 miles per hour. These pieces of ice and rock constantly collide with one another. Some form small moons, while others break apart. However, they never grow larger because Saturn's massive gravity tears them apart. Scientists are just beginning to understand how these rings formed. One theory suggests that a comet struck a moon, knocking it out of orbit and closer to Saturn, where the planet's gravity shredded it into pieces. These remnants became trapped in rings orbiting the planet. However, the real mysteries of gas giants lie deep inside them, tens of thousands of miles beneath their clouds, in an environment so extreme that it defies the natural laws we understand. Most of the newly discovered planets orbiting distant stars are massive gas giants, so large that they make Jupiter seem small in comparison. But no one knows what happens inside gas giants, whether they are in our solar system or far beyond. We know that Jupiter's thick atmosphere extends 40,000 miles deep, with bands of gas moving at high speeds, creating violent storms on its surface. But what lies beneath those storms is still unknown. NASA sent the Galileo spacecraft on a 14-year mission to Jupiter to uncover its secrets. On December 7, 1995, Galileo deployed a probe into Jupiter's atmosphere, entering at a speed of 160,000 miles per hour. As the probe descended through the thick air, parachutes slowed it down. It observed lightning in the clouds and winds blowing at 450 miles per hour. The probe sent data back to Earth for 58 minutes. What happened to the Galileo probe we sent in? It didn't hit anything, it just kept falling into Jupiter's atmosphere. The pressure increased steadily as it descended, measuring 23 times higher than Earth's pressure and temperatures over 300 degrees higher than on Earth. As the probe fell deeper into Jupiter's hydrogen-dense atmosphere, the pressure continued to rise, eventually crushing the probe. Although it only reached 124 miles below the surface before being destroyed, it provided valuable insights into Jupiter's interior. However, the planet's core remains a mystery. Like some rocky planets, gas giants also have magnetic fields. Jupiter's magnetic field is 20,000 times stronger than Earth's and so vast that it stretches all the way to Saturn, more than 400 million miles away. Like Earth, Jupiter's magnetic field protects its atmosphere from the solar wind. Upon examining Jupiter's magnetic field, scientists discovered that it also affects Jupiter's moons. The volcanic moon Io orbits just 217,000 miles from Jupiter. Every second, Io's volcanoes release a ton of gas and dust into space, amplified by Jupiter's magnetic field, which creates powerful radiation belts. This makes the area around Jupiter incredibly active. If you point a radio antenna at Jupiter, you can hear how the planet's magnetic field interacts with its environment. Jupiter and Saturn can even produce auroras without needing the solar wind. Their immense size allows them to generate their own magnetic fields. These auroras demonstrate that gas planets also have magnetic fields, but how are they generated? On Earth, the magnetic field is created by a hot, liquid metal core spinning around the planet's solid iron center. Gas planets likely have a similar process, but they lack the hot iron cores found in rocky planets. Instead, they formed around frozen cores of dust and ice, so we're not entirely sure what's happening inside. We don't fully understand the deepest parts of Jupiter's interior. It might have a solid core at its center, or it could remain entirely liquid. We may never know, as no probe could ever survive the 44,000-mile journey to Jupiter's core. Gravity and heat play crucial roles in shaping how planets evolve, from their cores to their outer atmospheres. They are the great forces behind planet formation. However, one more essential ingredient significantly impacts how planets develop: water. While planets may appear fixed and unchanging, they are constantly evolving. One planet in our solar system lost its atmosphere and turned into a desert. Another planet got too hot and became a planet from hell. Planet Earth has also changed, and it was water that changed the game. When you look at Earth from space, you can see a lot of water. After all, we are the blue planet. That makes it seem like Earth must be very wet, right? At first glance, our world appears to have a lot of water, since 3/4 of it is covered by oceans. But that's not entirely true. Only 0.06% of Earth's mass is actually water. Some of it is on the surface as oceans, and some is trapped in the rock. But in reality, Earth is a relatively dry planet. All of the inner rocky planets, including Earth, formed close to the Sun, so they started off dry. Any water they might have had either evaporated or was blown away during collisions that formed the Earth. These massive impacts were so energetic that any water would have evaporated and left the planet. So, where did Earth's current water come from? The answer likely lies with asteroids and comets. When you look at the gas giants, Jupiter, Saturn, Uranus, and Neptune, you see they have a lot of water locked inside them. Even more dramatically, at least half of the water on the moons of these planets exists in some form. So, how did some of this water get to Earth? The most likely explanation is that there were asteroids and comets in our solar system that were far enough from the Sun to retain their water. Millions of these water-rich asteroids and comets bombarded the inner solar system, with some crashing into Earth. Over time, this is how Earth acquired the water that now covers much of its surface. Without this surface water, life as we know it wouldn't exist. But what if there were too much water? The oceans would be so deep that they would cover the continents, including Mount Everest. It's likely that Earth's precise amount of water is what allowed Homo sapiens to evolve into a technological species. About 4 billion years ago, a blizzard of comets and asteroids delivered just the right amount of water to Earth. This is how the planet we know today came to be. It's possible the same process is happening somewhere else in the universe right now. There's a lot of water out there, that much is certain. The most common atom in the universe is hydrogen, and oxygen is not far behind, making H2O a very popular molecule. Water is everywhere in the universe, and we're discovering more and more planets. However, we haven't yet found another planet where water exists in liquid form. Over 400 new planets have been discovered by scientists, but none of them look like Earth. What we haven't yet found is a planet around another star that is about the same size, mass, and composition as Earth. It remains an extraordinary goal for humanity to find another world that reminds us of home, but we will keep searching. We know our galaxy alone has around 200 billion stars, and up to 40 billion of them may have their own planets. We are entering what will be called the golden age of planetary exploration. In the near future, we'll begin to understand just how different things are out there. It's going to be a very exciting time. The laws of physics and chemistry explain how planets are formed, and many scientists believe it's only a matter of time before we find another planet like Earth, one that formed from the same materials, in the right place, and with the right amount of water. One thing is certain, there are billions of planets out there waiting to be discovered.